All right, so welcome to today's physics video. Let's see, we're going to be learning today about power, and by the end of the video you should have a good conceptual understanding of both average and instantaneous power. All right, and then you should be able to solve problems dealing with both of them, average power and instantaneous power. All right, so here we go. Power. All right, so the symbol for power is a capital letter P. Power is defined as the rate at which work is done. And because there's this sort of connection between work and energy, we can also define power as the rate at which energy is transferred from one form to another or from one object to another, okay? I'm now wondering if I spelled transferred right. I'll have to look that up. All right, so to calculate the average power generated is the way that we say that. We say that power is generated, or sometimes power used. Could you say power used? I guess you could say power used. So to calculate the power generated by an object, you calculate the work that it did, and you divide it by the time that it took to do that amount of work. All right. Like I said, sometimes you'll see me write this. Work is, a change in energy of some form, right? So sometimes you'll see me write it this way: change in energy divided by the time it took for the energy to change. Okay. So probably easiest to just do an example. So here we go. So Roy lifts a 20 kilogram box up 3 meters in 4 seconds. So here's our 20 kilogram thing. It starts, we'll assume, at a height of 0. We're going to lift it up. 20 kilograms. So now the height is 3 meters, and this took a time of 4 seconds. All right. We can, as we usually do when we lift an object, assume that it starts and ends at rest, right? So, to find the power, average power, I guess I should specify, to find the average power, we're going to take the amount of work that Roy did and divide it by the time it took. Well, the work that Roy does is equal to, he's the only non-conservative force in this scenario, so the work that Roy does is equal to the change in total energy, which for us is just a change in GPE, right? Oh, well, that's just MGH, right? So let's see, we're lifting a 20 kilogram thing. Acceleration of gravity is 9.8 meters a second squared. The height that we're lifting it is 3 meters. So multiply this out and you will get 588 joules. So that's the amount of work that Roy did. So to find the power, I'm just going to take the 588 joules worth of work that Roy did to give it that GPE. Notice KE is not even an issue because it starts and ends at rest. And divide it by the time, 4 seconds. So divide this out and you get 147 joules per second. All right, now notice, that is, as the symbols would imply here, it's an average. That means on average, Roy gives the box 147 joules each second. That doesn't mean literally 147 every second, it just means an average. Okay? All right, now, it turns out that power is a fairly common thing, and so this thing, joules per second, has a name. We call it watts. So 1 watt in the land of science, 1 watt, capital letter W, is equal to 1 joule per second. Okay? So for us, the average power that Roy generated lifting this thing was 147 joules per second. We can just write that as 147 watts. All right, please be careful. Work is measured in joules. Power is measured in watts. So there's 2 different W's there, different meanings. We know this is watts because it is after the number and thus is a measure, it's a unit. Okay? So there we go. That's the average power Roy did, 147 watts, 147 joules per second. Now let's do another example. All right, so this time, let's see, what are we given here? It says, how much energy will a 60 watt light bulb use if left on for 12 seconds? So 60 watts, that is a measure of the power of the light bulb. So that's 60 joules per second. This step here you don't have to do. I just find it helps me process what it means to break it down into units that are a little more meaningful. All right, and then the time is 12 seconds, and the question wants to know how much energy is used. So we're looking for the change in energy, right? Okay, so, well, if power average is change in energy per unit time, that means that change in energy is power times time. So for us, we're going to use 60 watts, that's 60 joules per second, for 12 seconds. Notice, seconds and seconds cancel, and we're left with 720 joules worth of energy that our light bulb has used. All right? Okay, so again, this was all average. Here you can assume that this is the average power used by a light bulb. Most of the problems we're going to do are going to be average, but occasionally I'll give you a problem where the power generated is not constant. All right, sometimes the power generated by a force is not constant, and if that's the case, then to calculate the power, you have to. So what you'd be looking for there is the instantaneous power. So this is instantaneous power. Okay, so if it doesn't, notice it doesn't say average here, so that just means the power at an instant. So the power at an instant is equal to the amount of force, the magnitude of the force, times the magnitude of the velocity, times the cosine of the angle between those two vectors. So if your thing is moving this way and the force is this way, then here's your angle. Okay, very similar to the force and displacement from work. All right, so this problem's a little interesting here. I didn't give you maybe the most useful information here. So let's see what we know. So we've got a 30 kilogram box. We are pushing it with a force of 120 newtons for a time of 5 seconds. Notice I gave you the time instead of the distance. It doesn't explicitly say it. Let's assume that it's from rest. And that is my bad. I should have written that. So we'll assume that our V here is 0. Call it VI, I guess. All right, so A says find the average power. So basically, we got to figure out how much energy this thing, all right? Well, so for part A, I guess, here. So where do I want to write this? Part A. P average is work divided by time. So we know the time is 5 seconds, but we got to find the work, which means we need to either find the change in energy or we need to find the distance that the thing went, right? So I don't know how you want to do this. There's a couple different ways of doing this. In fact, it's probably worth your while. You know what? Pause it right now and figure out how much work this does. There's no one easy way to do it. It's going to be a couple steps no matter what. Okay? All right. So option 1 is to do this. Let's find the change in kinetic energy. Let's see. I ought to be able to find my acceleration. The acceleration is net force over mass. So 120 newtons is our net force. Our mass is 30 kilograms. That gives us an acceleration of 4 meters a second squared. And if we start at rest, that means that my final velocity is going to be VI plus A times T. So 20 meters a second, right? And now I can find my kinetic energy. So I guess at this option, you can either find your change in position and then do force times displacement, or find your kinetic energy. So I guess this isn't really, well, All right, so we'll finish this. Okay, so, sorry, so our kinetic energy final is going to be half of the mass times the velocity squared. So 20 squared is 400 times 15 is what, 6,000 joules? Okay. Option 2 would be to find your change in position, which would be Vf squared minus Vi squared all over 2a. So that's going to be 20 squared minus 0 squared all over 8. So 20 squared is 400, so that's going to give you 50 meters. And then work equals force times displacement. So our force is 120 newtons times 50 meters. And that also gives you 6,000 joules. Okay, so no matter how you slice it, the work done is 6,000 joules. The time this took was 5 seconds. So multiply it out and you're going to get, what, 1,200 joules per second, or 1,200 watts. So there is our average power. Okay. All right. Now, parts B and C say to find the power Roy is generating after 2 seconds and after 4 seconds. So again, we're not gaining, this is how much energy you gain per second on average, but because the speed increases, the rate at which your displacement increases, I said that badly, but so the amount of energy you gain per second gets bigger and bigger as you go faster and faster. Okay, so up here, let's see, find the power Roy is generating after 2 seconds. So now we're looking for instantaneous. So power is force, which is 120 newtons, times, let's see, the velocity after 2 seconds. Well, we found our acceleration here. It was 4, right? So that means after 2 seconds, our velocity is going to be 8 meters a second. Both the push and the velocity are in the same direction, so our angle is 0. So cosine of 0 is just 1. So multiply 1200 times 8 gives you what, 960 watts? And the units do work out. You get Newton meters, which is a joule per second. Okay? And after 4 seconds for part C, we've got the same force, but now we're going faster. So you get, what, 1920 watts? Okay? And the power is increasing because the velocity increases. Okay? And how would the problem change if this force was exerted at 60 degrees below the horizontal? Well, then your power and your work would all be, times the cosine of what, 60, right? Because this force would be this way, and your displacement would be that way, right? And cosine of 60 is a half. So all of your answers here would have been half as big. Okay? So there you go. That's power. Not much to it. All right. So, I guess that's it. How do I stop? Stop.